Let's start. Everything works over there? Yeah, okay. So, hello, my name is Warski. Thank you very much for coming. I would like to do today a comparison between Akka, ZIO, and Monix in the field of concurrent programming. So, there will be a couple of introductory slides, and then we will proceed to the code. I know it's late, but I hope the code will wake you up. So, what do I mean by concurrent programming in 2019? Well, when we want to do something that processes data concurrently in parallel, we typically have to define a couple of processes that work on the data, that communicate with over the network, that read some data from the database, and so on. So, of course, the question is, how do we define these processes? And there's a couple of answers out there, especially in the Scala land. Historically, Scala, I think, had quite a lot of success, and the scalability of the language allows you to define some really nice APIs for defining these asynchronous, concurrently running processes in a nice way, and in a way that makes the programs easier to write and also have less bugs as an effect. So when wondering how to describe, how to define these concurrently running processes, we have a couple of questions to answer, right? So the first thing is, how do we compose processes, right? So we typically want to run a couple of those, maybe concurrently, maybe in sequence. So the first aspect of the API is, how does it allow composing a couple of processes together, right? Processes also typically communicate with each other. So a very important aspect is how one process can communicate and can send data to another process. How can it communicate that it's done, or that it needs more data, or that it needs to spawn child processes, and so on. Finally, the hard thing in concurrent or parallel programming is managing state, right? We cannot access the same and mutate, more importantly, the same state from multiple threads. So this state needs to be somehow protected, right? So that there's always only a single writer to our protected state. So in Scala, all of the libraries that we will look at constrain side effects in some way, and all of the side effects are always wrapped in some kind of a container. And these containers actually allow you to define and describe these processes in a flexible way. They allow you to work with values, which you can then manipulate, and the values are the means through which we create the processes, right? So these containers differ from library to library. So, for example, in the Akka land, we will mostly work with futures. A future is an eagerly running computation. It's important that it's eager. We'll see later why. So a future is a computation that's already taking place, right? On the other hand, we have various lazy implementations, such as tasks, IOs, and so on. And these describe a computation which will take place once we run it, right? So on one hand, we have the eager futures, and on the other hand, we have the lazy tasks, IOs, and so on. Okay, so this may sound abstract, but we will see concrete code in a second. So in our example, we always need some kind of an example. We will pretend that we will have a number of devices. These devices will be laser cutters. That's how they will be called in the code. So let's imagine that we have a series of laser cutters, right? And such a device is a scarce resource to which we have to protect access, right? We want to send lists of commands to a laser cutter. So you can imagine that a list of commands describes how to, I don't know, cut out a cat shape or a dog shape or whatever. So we want to send a series of steps to each of these devices. And of course, we must ensure that only one thread or only one process sends these commands to a laser cutter at a time, right? So we will communicate with these devices using a connection object, right? It's also quite similar to like a database connection. Here it will be a device connection. So this device connection object is the state that we want to protect in our processes, right? And of course, we can use multiple different laser cutters in parallel. but we want to protect the connection of each so that it's used by a single process. Okay, so we will have a number of processes which actually communicates with the devices, and we will have a coordinator process which will again store state. The state will be the list of free devices, of free connections that you might use. And if there are no free devices, it will also store a buffer of jobs to run, so a buffer of list of commands that's supposed to be run. So when we look at the code, so the goal here is not to become familiar with the API, because that's, I guess, best done, at home when you have the IDE and so on. Just to get a feeling of what are the main differences between the Akka approach and the more functional approach, let's say, right? So when looking at the API, take a look at how does the infrastructure code, so how does the code that we use to define the processes interfere with the, let's say, core business logic, right? Is it programmer friendly? So is it easy to read and to understand, right? If you show it to a colleague, would they understand it? Notice how the description of our problem is separated from the evaluation of the actual process, right? This will be an important difference. Also notice what is eager and what is lazy. That's I mentioned before as well. Okay, so before we actually jump to the code, a short introduction so that you know who's talking to you. I'm one of the co-founders and a software engineer at Software Mill. We are a consulting and development company. We specialize in Scala, Akka, Kafka, Cassandra, other technologies. We help companies scale up their businesses, introduce functional programming, event sourcing, data streaming pipelines, and so on. I'm also working on a couple of open source projects, such as STTP, Tapir, QuickLens, and a couple of others. Okay, so that's the first example that we will look at is we'll be using Akka. So we will be using Akka typed here. So you might be familiar with the traditional Akka approach, which uses bare untyped actors, right? And the messages that you send to an actor are always untyped. So here we are using Akka typed, which is an evolution of the framework. So just as a short reminder, an actor, which is the basic building block of everything in Akka, an actor is a lightweight process which contains some state, and that state is guaranteed to be protected. So it will always be accessed by a single thread at a time. The way you can communicate with an actor is by sending it messages. And these messages are also guaranteed to be processed one at a time, right? So the actor is a lightweight process, and it encapsulates some state. Okay, so let's look how can we implement our LaserCutter example using Akka. So as I said, we will have a device connection class, right? So we pretend that we have a number of LaserCutter devices, and we communicate to them using these instances of the device connection class, right? So that's like a database connection. Here we have a device connection. This class has a single method called run command, right? We can send a command like go forward or turn right to the device, and the device will execute that command, right? Executing the command will take some time. So we have an asynchronous interface, so we get back a future, right? That future will be complete once the device completes the command, right? Because we are pretending we don't have real devices, so instead of doing network I/O to the device, we will only do screen I/O, printing something to the console, right? So here's our side effect of actually sending the command, right? And in some cases, things will end up with an error, so an exception will be thrown and the future will be failed, right? So that's the interface to the device that we will be using. So first, let's and here's a type alias, which is a list of commands that we will be sending one by one to the device. So first, let's define the behavior of a process which will manage a single list of commands, sending a single list of commands to a single device, right? So that's a process to actually complete a single list of commands. So we will define the laser cutter process. It will take 2 parameters. The first parameter is the commands to execute. The second parameter is the device connection to use, right? The result of this process will be a behavior. A behavior is, in Akka typed, describes what the actor should do, right? So that's a description of the behavior of a single actor. Okay. What's important is that it's a lazy construct. It's a data structure which only describes what the actor should do, right? So by creating a behavior, we don't actually do anything except allocating some data structure on the heap, right? It's only a description. Nothing happens when you create it. Only once you actually interpret, once you pass it to Akka, it will create an actor with that specific behavior. So the behavior is parameterized with a single type, and that's the type of the messages which we can send to our actor. So here we will be sending 2 types of messages. So we are type safe, so we always need to define a closed set of messages that we can actually send to our process, to our actor. So we'll define a sealed trait laser cutter message. And the first kind of message will be next command. And the second will be error. Okay. So when our actor receives the next command message, it means that the device has finished executing the last command, and we should execute the next command, right? If the actor receives the error message, it means that there's been some error in the device and we have to abort the whole process. Okay, so the behavior of a single laser cutter process will be accepting these messages. So how can we create this behavior? So there's the behaviors the behaviors object in Akka type, which contains factory method to defining a number of behaviors. So one of these behaviors is receive message. And receive message describes a behavior, so it creates a data structure which describes a behavior, which specifies what should the actor do when a message arrives on its mailbox, right? So we can receive two types of messages. The first is next command. The second is an error, right? Okay. So now what should we do when the actor receives a next command message, right? So we should take a look if there are any commands left still to process, right? So we take a look at commands. If there either can be no more commands to process, or there can be a single command and some other commands. Okay. So let's take it one step at a time. So what if there are no more commands to process, right? If there are no more commands to process, well, we have to somehow stop the whole laser cutter process, right? That's the finish of the process. We have executed all the commands. So what we have to do is we have to somehow free the connection, right? So we have to tell the coordinator that this connection is actually free, and then we have to stop the process. So how do we do that? Well, if we look at the signature of the receive message method, it actually takes a function which, depending on the received message, returns the next behavior of the actor. Right, so it's similar to the FSM, the state machine actor, which you could also do in Akka untyped. So our description of our behavior is receive a single message from the mailbox and then decide what to do next. Like, what's the next behavior of the actor, right? Here, the next behavior of the actor will be quite simple. Behaviors.stopped. It means stop the process. Okay, so now. If there's an error, we will actually do the same. And we'll just print line, then there's an error. And we'll return behaviors stopped. This one. Okay. So now, and we also have to free the connection over here. So now, the last case, what do we do if there is a command to execute? Well, we take the connection, the only thing that we can actually do, and we run the command, right? We run the command, and at that point, because we get a future, right? Here we get back a future. So that's a process which already is running in the background, right? So it's an eagerly running side effect, right? So in our lazy description of the behavior, we can actually do some side effects. And here, that's one of the side effects that we do here, right? So we run the command, but then once the command is complete, we have to tell the actor that it should process the next message. So what do? We say that on complete, and there are two cases. It can either send, the run command, right? It can either complete with a success or it can end with a failure. Okay? So now if it ends with a success, what we have to do is we have to somehow obtain the self-reference of the current process. So we have to tell the self and send ourselves the next command message, right? Here, similarly, we have to send ourselves an error message, right? So now the problem is, where do we take the self-reference from, right? Remember that we are only creating a data structure, a description of how the actor should behave, right? We don't actually live in any kind of context from which we can take the self-reference, right? So we actually have to include in our description the fact that we want to extract the current context in which we are running. And we can do that using the behaviors.setup method, passing in the type here, otherwise type inference is lost. So we wrap our receive message behavior in another behavior, which says extract the current context in which we are running, and receive the next behavior of the actor, which is receiving a message, right? And here we actually get the self-reference from the context, right? It's still red. That's good, because we still have to return the next behavior of the actor, right? So what we did is we said, if there is a command, actually run this as a side effect, right? So that's a side effect, something happening in the background. But what should the actor do now? It should, again, receive the next message, right? So when the future completes, it will actually get the next message, right? So what we have to do is we have to recursively call the LaserCutter method with a shorter list of commands and the same connection, okay? And that's it. Okay. So far, so good. Well, we still have one hole here. We have to somehow free up the connection, right? So once we have executed all the commands in sequence, right, we have to say to the coordinator that we are done. So to do that, we will actually the coordinator will be another actor. So I will just copy the messages over here. The coordinator will be an actor which will receive messages of type coordinator message. And we can send two types of messages to the coordinator. The first one is that the connection is free. And the second is that some commands should be scheduled to be run by the coordinator, right? So here we will need to add an extra parameter, which is a reference to the coordinator actor. Coordinator message, okay. Right, so now our LaserCutter process is parameterized with the reference to the coordinator actor, right? We have to pass it here as well. Coordinator, okay. And here we can actually now run the side effect of freeing up the connection, and that's simply coordinator send connection free of connection. Right, and we copy that in case of an error as well. Okay, so now we have described the process of a single LaserCutter running as a list of commands, right? So we have a list of commands which we run in sequence by by sending them to the connection, and we create a description of the behavior, right? These are all these are all data structures which we create, and then they will be interpreted by the actor system. So now what we will do is we will actually implement the coordinator using the functional approach. So I will just copy the the coordinator code using Akka over here, because we don't have that much time, unfortunately, it's fairly similar to the process we have seen before. It uses the same constructs. The coordinator holds state, as I said. The first element of the coordinator state is the list of free connections, right? And the second element of the coordinator state is the buffered list of commands that have to be run. And the task of the coordinator is pairing up a free connection with a list of commands, right? So the only important thing really that happens in the coordinator is over here. So once we actually have a pair, so we have a free connection and we have a list of commands, right? What we do is we create a child process, is we create an actor using a specified behavior, right? So first we create the behavior. We invoke the LaserCutter method over here, right? So this creates a description of the behavior, and then we pass it to the spawn method, which actually creates an actor with that behavior, right? So that actor will actually go step by step and see, what should I do now, right? That's my behavior, so I will do that, right? And so on and so on. Because each behavior results in a new behavior that the actor should actually do. Okay, and then we kickstart the whole process using the next command method. So we can, so that you can see that it actually works, we can have some example data over here. So what we do here is that we create an actor system. So an actor system is like a thread pool, but in Akka typed, it also needs to have a top-level actor. So here the top-level actor is a coordinator. Again, we create a description, we pass it to the actor system, and the actor system creates an actor which will execute that behavior. We create some device connections, right, and we run the whole thing. So we may see if it actually works. We are scheduling a couple of lists of commands to run. And yeah, the side effects that we have created are just printing to the console, so we can see that this is actually being run first by the second connection, then by the first connection, right, the LC1 and LC2. Then there's an error because there's no turtle, right? So we have an error here, but things continue running, and we are processing other things as well. Okay, so that's the Akka example. So now let's move to the second one. Despite the title said that I will actually compare both Monix and ZIO, but that would take too much time, so I decided only to do ZIO. However, in the scope of this example, the code using ZIO and the code using Monix would be almost identical. You would have to switch IO to task, and it will be more or less the same. So the distinguishing thing, the important difference between ZIO code and Monix code is that in ZIO, errors are also typed, and in Monix not. I will show you exactly where that place is, so that you know the difference between Monix and ZIO in the scope of this example, right? There are many more differences, but in this example, that's the one that would be actually visible. Okay, so now we are moving away from the future world, right, to a more functional world. In the functional world, everything is lazy, right? Before we had lazy behaviors, but the futures were running eagerly, right? Here, everything is lazy. So we have the same device connection class, which is used as an interface for our connection. We have the same run command method, so it accepts a command, and what it returns is an IO type, right? An IO type is, well, it's like a future in some ways, but in more ways, it's not like a future. So an IO type is a lazy description of a side effect. So again, it's a data structure, which, when actually interpreted, will run the side effects, right? So a future is a computation running in the background, and an IO is a lazy description of what will happen when we actually execute the side effect, right? So here we have like a functional interface to our device. The effect is the same, right? We wrap it in an IO constructor, so that will be evaluated lazily. It's a biname parameter. The effect is the same, just printing to the console, right? So that's again the same. Again, the important difference here is the typed errors, right? In the future case and in the Monix case, if there's an error, so if the asynchronous computation fails, the errors are always typed as an exception, as a throwable, right? In ZIO, they make a distinction between errors that you expect to happen, so errors from which you can recover from. So here we actually expect that from time to time there will be a LaserCut exception, right? And of course, you can always throw other type of exceptions, but these are considered to be bugs, right? These are errors which you actually do not expect and you cannot recover from. And these errors you expect are typed. Okay, so let's first again implement the process of a single laser cutter, the single laser cutter process. So we define a laser cutter process. Again, it's parameterized by the same things: a list of commands and a connection to use. It will return a description of a process, which will either throw a laser cutter exception or return a unit. Okay, but now we can do something a bit different. So we have the list of commands that we have to run, right? And now what we can do is we map over this list, like you map over lists quite commonly, probably, and we can map and create a list. We can map using the run command method, right? So now we had a list of commands, and what we get is a list of descriptions of how to send the command to the device, right? We can do this because these descriptions are lazy. If we did it with a future, they would all be sent at once, right? Because we would create a list of futures, and the futures is a running computation, so all the commands would be sent to the device at once, and it would blow up, right? So here, we are only creating a list of descriptions, and that's the important difference. And we can do it safely, right? So now what we want to do is we want to say, run this list of commands in sequence, right? That's a common thing. So they actually have an operator for that called collect all. The collect all takes a list of descriptions of side effects and returns a side effect which will run these side effects in sequence. So then we have to discard the result, so we get a unit. And that's the implementation of our laser cutter process, right? It's quite significantly different from the actor that we have defined before. Okay, now, once we have that, let's actually implement the coordinator, okay? So our coordinator will have a list of initial connections, device connection, okay? And it will return a description of a process which cannot fail. So we don't expect it to fail with any kind of errors, and returns a result which is more like a technical thing so that we can actually communicate with the process. So don't worry about that. Okay, so now how can we implement the coordinator? So in Akka, we actually have a single template, a single blueprint for an asynchronous process, right? Each process that we define in Akka is an actor with which we can communicate using messages, right? It's a very useful template, it's a very useful blueprint, but it's not always the only answer, as we have seen, right? For example, the laser cutter process over here didn't really need an inbox, didn't really need the whole actor decoration, right? So in ZIO, we kind of have more flexibility. In Akka, we only have this one blueprint that we always use. That may be a good thing, that might be a bad thing, right? Because sometimes if you are constrained, it's actually easier to do things. In ZIO, we have more freedom, which means we can implement processes like we have done here with the laser cutter, right? In a very second way. But sometimes we actually have to kind of implement an actor, right? So in case of a coordinator, we actually do want to have a single process which has encapsulated state and with which we can communicate by sending messages, right? In Akka, this is built in. This template, this actor and this messages template is built in. Here, we have to explicitly create a queue, which will be the inbox used to communicate with the actor, okay? So to implement the coordinator, we will actually define two methods. The first one will describe a process. What should the coordinator do, given some state of free connections and waiting messages? So it will have a couple of parameters. The first one is the inbox. So that's the way to communicate with the process, right? In Akka, that's like provided by the framework. Here we have to do it. Here we have to explicitly write that we need a queue of coordinator message. Okay. The second process will be the connections that are currently free. That's a list of device connection. Okay, and this third parameter is the waiting comments, right? Okay, and it's a description of a process, no errors in the unit. So what we do, again, is we take a look at the connections and the waiting jobs, right? And now we have two possibilities. Either we have a match, so there is a free connection. You can call it free connection and some other connections. And we have a first waiting job, and other waiting, right? We pattern match on the connections and waiting jobs. So, well, in that case, we have like a pair, right? We have a free connection, we have a job to run, so we can actually start a process which actually does that. So what we do is we call the LaserCut method. We pass it the commands to run and the connection to use, right? So what do we do now? Well, we have a description of a process, but it throws some errors, right? And here we need to handle all errors. So what we do is we actually handle the errors over here. So we use the catch-all combinator, and we say that if there's a LaserCut exception, we will just print line something to the console, right? Okay. Okay. So you may notice that I've wrapped this in an UIO. A UIO is an IO with the first type parameter equal to nothing. So in ZIO, every side effect needs to be controlled, and every side effect needs to be actually wrapped in the container, right? In Akka, we could have run any side effect as part of the handling the message. Here, every side effect has to be, well, it's not enforced by the compiler, but the idea is that every side effect is managed and is wrapped in an IO data type. Okay. So we have a LaserCut process description. So now what we need to do is we need still to free up the connection, right? Notice that we don't free the connection over here in any way, right? So what we need to do is we need to always free up the connection, regardless if the LaserCut process ended successfully or with an error, right? So again, there's a combinator for that called ensuring. And ensuring takes an effect to run always when the process finished, right? So the effect that we want to run here is we actually want to send, let's say, that's not like, again, that's how we model things here in our code, but that's not something enforced by the framework. We are creating an effect which will actually put a message on the inbox, and the message will be connection free, right? The free connection. Okay. So again, the ensuring over here, it takes a finalizer which is also a lazy description of a side effect, right? Every side effect is wrapped in an IO, right? So here we again have an IO. And because we are using a queue implementation from ZIO, the offer method, actually, when we call the offer method, it doesn't actually put anything on the queue. It returns a description, which, when executed, will put the thing on the queue. Okay, so everything is lazy. But thanks to that lazy approach, we can actually create this process and enrich it step by step, right? So this description over here, right? It's not something that's running, so we can safely and without fear like enrich it in multiple ways. It's only a description which, once we pass it to an evaluator, will run, right? Okay, so we have freed up the resources. So one last thing that we need to do is we actually need to run this in the background, right? Because we are in the coordinator process, and we now have to say that we have created a new description of a process and run this in the background. So we create a fork. We use the fork combinator, right? So what this does is it creates a new description, right, which says I'm wrapping this description over here, run, right? And when you interpret this, fork and run this description of the process in the background, okay? And finally, we need to do something in the main coordinator process. And what we do in the main coordinator process is we call the receive method, which we'll write in a second. Other connections, other waiting. Okay. Okay, and that's it. And if there is no match, then we simply call receive inbox connections waiting. And these receive and next methods are mutually recursive. So the receive method actually has the same signature, and it's a bit simpler. Receive. Okay. So what receive does is it takes the inbox. We take the inbox. We take the first message from the inbox. And now, depending what the message is, it can be either connection free connection. Then we call next inbox. We add it to the list of free connections, and we decide what to do next. Or it can be run commands. Commands. Next inbox connections commands waiting. Okay, it's type checked. And finally, we need to bootstrap the whole thing. So we create an inbox. We create an unbounded. Well, that's not what I wanted. We create an unbounded inbox which will hold messages of type coordinator message. We kickstart the process, so we create a receive process with the initial connections and no waiting methods. And now we want to run this process in the background, so we use the fork combinator, and we yield a coordinator result, inbox fork. Okay, so that's the description of our coordinator process, right? This description, what it will do, what it will do, thanks. It will create an unbounded queue. Then it will create the receive process, and it will run it in the background, and it will return control to the parent process which called it. So now let's copy some test code over here. So in our test code, what we do is we have a default runtime. So that's in actor systems. In Akka, sorry, we had the actor system, which was like the default interpreter for behaviors, right? So it took a behavior and it returned an actor. So here we have a default runtime. So what it does, it takes a description of a process and it interprets this process, right? Step by step, right? Each time we use a combinator over here. So when we call ensuring, when we call fork, we create a new description, so a new data structure, which is bigger and bigger, right? But it contains instructions to what the runtime should do when evaluating this process. Right, so in our runtime where we create the coordinator, and then we use the inbox, which is returned as a result to actually send some commands to our process, so we can actually run this. And yeah, the output is fairly similar, right? So we have some commands are processed by the first connection, some commands are processed by the second connection. There's the error, as we have seen before. So this works more or less the same. The order is probably different. Okay, so that's the code. So as for like the main features, where we have and the main differences between the future stack and the functional stack, let's say. So in Akka and Akka typed, what we have seen is we have descriptions, which we have behaviors, which are also descriptions. They are lazy descriptions of how an actor should behave. They are typed, so we have to explicitly specify the type of the messages that we can send to the actor, right? However, the side effects that we execute as part of the actor behavior, these are usually future-based, so they are eagerly evaluated, right? So in Akka type, we have kind of a mix. We have the lazy behaviors and the eager futures, right? Both in Monix and in ZIO and in Cat's effect, everything is based on lazy data structures, which are evaluated only once we actually interpret them, right? So this also means that when defining these processes using ZIO or Monix, we actually have to define one big process which describes all of the side effects, right? So we cannot describe part of the process and then describe the second part of the process separately. We have to somehow connect them so that they are part of the single evaluation. All of these approaches are type safe. The difference being that in ZIO also the expected errors are typed, right? In Akka and Monix, these are typed to throwable. I also already mentioned the side effects. Lifecycle of callbacks is also quite important. So how do you handle errors? How do you handle finalizers? So in Akka, this is typically done. We have done it kind of in a manual way. So if there was an error, we were just sending an error message. Another way in which you can try to do that is using supervisors. So you can create when you create a child actor, you can supervise it and be notified when the child actor is terminated. However, the behavior, so the things that you do when you receive a lifecycle callback, this needs to be synchronous, right? In ZIO and in Monix, everything is based on IOs, which again are, so it's the same construct, right? It's the same description of side effects. And also an important difference is that in Akka we have the single blueprint of an asynchronous process, which is actors. And again, that might be a very good thing because it simplifies the way you think about asynchronous process, right? It's always an actor, and you always know that you are going to communicate with it by sending messages. In ZIO and in Monix, we have more flexibility, but with more power comes more responsibility. So, we have looked only at a very small part of all of these libraries. So Akka is much more than just the actors, right? We have Akka persistence for event sourcing, we have Akka clustering, Akka remoting, and Akka streams. In Monix, we also have an reactive streams implementation and quite tight integration with Cuts effect. In ZIO, we have software transactional memory, we have execution traces, we have a DSL for defining retries, also Cuts integration. So there are whole ecosystems built around these libraries. We have only looked at a tiny fraction. So depending on what we actually want to do, you should probably look at the whole add-ons that are available. Okay, and that's all I had. If you would like to take a look more in more detail, this block over here contains a detailed comparison of Scala ZIO, which is now ZIO, Monix, and Akka typed with a couple of code examples. So it's like a three-part blog. The code for this presentation is online, and yes, please visit our stand. You can subscribe there to Scala Times, or you can win, or you can rather try to win. Try to win an entry ticket to our 10th birthday party. If you have any questions, I'll be happy to take some. That would be a hard question.
Thanks, Adam. Great presentation. And thanks for giving the Akka example. I think you have shown with the laser cutter a perfect example for how I think actors should not be used for processes. The coordinator was a perfect example for how actors should be used, but for processes, I think actors are too cumbersome. As we have seen in ZIO, it was a one-liner, and the Akka actor process, LaserCut process, was like 20 lines and sending messages all around. Right. I think there are better ways using Akka streams, or maybe even futures. Even though they are eager, you could somehow make them.
Right. Yeah, you can.
Map the futures
well, if you try to make the future not eager, you actually end up doing a very simple version of an I/O because you create a wrapper which contains a lazily evaluated future, right? So we can do this as well.
Something like that, yeah.
And yes, I agree that Akka streams would fit here as well. Yeah.
Okay.
But if you want to do it with pure actors and I guess that's where you would have to do it.
So we have all seen that actors are not a silver bullet and don't overuse actors. I love Akka, but don't use actors for everything. Thanks.
So yeah, you're saying that ZIO is more powerful than Akka. I mean, like has more power. But if you look at an Akka actor, you can just change the behavior while running, going to a next step. So that seems like extremely powerful. So you can just, while going to the next step, take a whole different behavior and completely change your program for each step.
Right. Well, I wouldn't say that ZIO is more powerful, really. Like maybe some things can be expressed in more concise code, and the whole approach when you switch to thinking in terms of lazy effects instead of eagerly running effects, well, this changes the way you code a bit, right? But I wouldn't say it's more powerful. As Heiko mentioned, if you combine Akka, especially with Akka streams, Akka clustering, and so on, so that's also quite a powerful mix. As for the changing behavior, well, yeah, actually that's a similarity, right? Because in both examples, what you do is you describe a single step of a process, like the behavior is a single step. I receive a message, and that's a single step, right? And what do I do next, right? So that's kind of changing behavior, but in a controlled way, because you always call yourself recursively. There's no mutable state or anything like that. In the ZIO example, we kind of did more or less the same thing, right? Because we also there was also the recursive step over here, right? Where we call the next method, which describes a single step of what should we do with this state, and the next step is described by a recursive call on the receive method. So these are quite similar. They are both implemented in a recursive manner, both coordinators. And if you actually look at the code of the coordinate over here, like even if you look at the shape itself, it's quite similar, right? We have the next and receive methods, right? And here we have two cases of a recursive receive call, and that's more or less exactly the same as we have here, right? Same with the handing of a single message.
Okay.
Okay, so thank you very much. If you would have any more questions, I'm here until the end of the conference, so feel free to ask. Thank you.